It's better now. All right. Shall we start? Good afternoon and welcome to lecture 6. So today I'm going to finish the remaining parts for the lecture 5, which is about the frequency selective circuits, RLC circuits in parallel and series, and the L, pi, and T matching networks. And then I'm going to continue on lecture 6 about the LNAs and the mixers. So today my plan is to finish the remaining part of lecture 5 and finishing the lecture 6. And then next week I'm going to solve the few questions on lecture 5 and lecture 6, and also the questions on the assignment. Any question from the previous session on a Smith chart and networks? No? Okay, if there is no question, then I start on frequency selective circuits, which are very important elements in the RF systems. We use them not only for the matching circuits, but also for reducing the noise figure, for increasing the stability of the circuits, and improving the power transfer ratio. So if I want to just have few definitions, quick definitions that maybe you already know about the frequency selective circuits, we have the Q factor and we have the bandwidth. So these two are two parameters that we use to characterize the circuits, especially those who has resistance and reactance. So if we say that to have a maximum power transfer to a load from a source, we saw in lecture 4 that we need to have a conjugate impedance from the source and load. I mean that for a circuit like this, that this is the transmission line, and this transmission line is Z0, and then we have a ZL which connected to a source Vs with the impedance of Vs. Then we say that from this section the impedance that we look into this network is Zin, and for the maximum power transfer we always said that Zin should be Zs conjugate. So this is what we proved in lecture 4. And then we define Q factor or quality factor. Actually it's Q here. Quality factor Q as the ratio of the power or energy which is stored in the circuit divided by the energy that we lose. Okay? I mean that if we have a circuit like this, if we have a network like this, and this network has one or many lossy components, then those components in each cycle, they consume some amount of power. So the power that we deliver from our source into this network, then some part of that is going to be lost in the lossy components, and then some of them is going to be stored inside the inductor and capacitors inside this. And then we define the Q factor as the average of the stored energy divided by energy lost energy per cycle. Okay? And this is the exact definition of that. At resonance frequency, I mean, we will see in the next slide that what's the meaning of resonance frequency. At the resonance frequency, the stored energy divided by power loss. And then we define the bandwidths. For example, the 3D bandwidths, the 10 dB bandwidths. This is per definition. The 3D bandwidth is the bandwidth that the attenuation is, the difference between the upper and lower frequencies. Attenuation is 3 dB. So if this is your, this could be V or this could be I, no difference. And then if this is your F, so the circuit that you see, and here is your resonance frequency, then we say that at your resonance frequency you see a value, and then 3 dB less than that means half of that, anything that you see. So these two frequencies, F1 and F2, or F lower and F upper. So the difference between these two is the 3 dB bandwidth of this system. I believe these are repetitive materials. Okay? Is it clear? Okay. Now for a general case of RLC in parallel. So assume that we have a R, L, and C, and these are pure R, pure L, and pure C. And then we are going to excite this circuit with a current source, and this current source is coming from this equation. I in equals to Im, which is I max, and then cosine omega t. So this circuit is working in the frequency of omega t, and frequency of omega, and then it has a maximum current of Im. Then the voltage across your load, or R, we can say that this voltage is coming from this formula, and Z is the input impedance of this circuit. Okay? So the voltage across this point and this point comes from the impedance of this circuit multiplied by the current that we feed into that, or the current divided by admittance. All right, which comes from here. And then we call it as this is coming from this formula, which has an amplitude and a phase shift. Depends on the value of the L and C, it has a phase shift. Okay. So the admittance of this circuit, we can calculate the admittance of this component, and this component adding together. So the admittance of R, the admittance of C, and the admittance of L. And we say that the admittance of this circuit is this way. So if we look at the V out and assume that we have we write the feed current as a phasor form, then we see that the maximum value for this voltage coming when this part, the denominator is minimum. The absolute value of this denominator is minimum. And the absolute value of this denominator is minimum when this part is equal to 0. Do you agree with me? Okay. So the Vm, or the Vmax, the maximum voltage, is coming from the only R multiplied by Im. And then this is the definition for the resonant frequency. At the frequency that our voltage is maximum. So this circuit transfers the maximum power into this load. Okay? And then we say that from this we can find the resonant frequency, which is 1 over the square root of LC. And then the quality factor that we defined in the previous slide, which is divided by Q divided by omega W of store divided by pi of loss. So W of stored is coming from the amount of energy that we store in the capacitor or in the inductor, no difference. We can take one of them because they usually change the energy between each other. Okay? And then the power which is lost inside the R, because R is the lossy element. Okay? So the power is lost we know that the power is 1 over 2 real part of VI conjugate. Okay, and then it comes from here. And then we define the Q factor or find the Q factor as these equations. We usually take this one because it's easier to memorize. So the Q factor of a RLC circuit is omega RC. And then based on the definition that we had for the bandwidths, we say that the bandwidth equals to resonant frequency divided by Q factor, which is this formula, and then the omega 1 and omega 2 can be calculated by this amount. Okay? You can easily put the V, or you can easily put the V is V divided by a square root of 2 and find the omega. What's the value for them? It's an equation, you can solve it. This is the graph that I told you. So at the F naught, or at the resonant frequency, we have the maximum voltage, and then at the F1 and F2 we have the RIM square divided by a square root of 2, and then this section, I mean from here to here, we say that this is the bandwidth. Any question? Okay. The same scenario we have for the RLC in series. So if we have, again, a circuit with the pure R, pure L, and pure C, and then we define to excite this circuit with the voltage source, and this voltage source equation is coming again from this. I mean, it has a maximum amplitude of Vm, and it's operating at frequency of F or omega. Then the current which passing through this circuit again is, if we look at the impedance of this circuit Z in from this point, we can say that the current which passing through this circuit is coming from this equation, V in divided by Z. And again, this has a amplitude and a phase shift based on the value of L and C. So this is Z. This is Z. And then the impedance of this circuit is, again, the impedance, the series of all these, the impedance of R, impedance of L, and impedance of C. And easily, again, we can write down this. And the value for I out, if we write down the voltage in a phasor format, is V divided by Z. And again, we say that the maximum current that we can get from this circuit, which is Im or Imax, is when the denominator, the absolute value of this denominator is the minimum. And the absolute value of this denominator is minimum when this part equals to 0. So at this frequency, I mean when this condition satisfies, or at this frequency, then the maximum power will transfer to the R, the load that we have. Okay? Again, we define the quality factor based on the definition that we have. The stored energy inside the L, we can write down as 1 over 2 Li squared. And then the power which lost inside the resistor, we can write down like this. And then again, we find a Q factor based on all these. Again, I said that this one is the most easiest one. So the quality factor of a series RLC is 1 over omega RC. So for the parallel one is omega RC, for the series one is 1 over omega RC. Okay? Again, based on the definition of bandwidths, which is F naught divided by Q, we find that this is the bandwidth of the RLC circuit, RLC series circuit, and if we look at the I over F, here I over F, we see that the maximum current that we can get is Vm over R, which I already find here, and then the 3 dB less than that one, which is half of that, or 1 over a square root of the voltage, then we say that this is our bandwidth. And the omega 1 and omega 2 is calculated from these two formulas. Any question? Okay. So now we are using these ideas to do the impedance matching from a load to a source. I'm doing this for pure resistive source impedance and pure resistive load impedance, and then at the end I tell you that if it's not pure resistive, I mean if it has some reactance, then what we should do, okay? So assume that we have a pure resistive RS and pure resistive RL. This is, assume, for example, this is 50 ohm, this is 100 ohm, and I want to match these two in such a way that the maximum power transfer from the source to our load with only reactive components. I don't want to put any kind of resistor here, because resistors are lossy and they consume power. So just by the reactances, which stores energy, I try to match these two resistance together. Again, going back to the condition that I mentioned at the beginning, if we assume that we add two reactances like this, one in series and one in parallel, this is general. I will say that what will happen if, for example, this is the other way. So if one in series and one in parallel, and this is the simplest format, I mean we call it L format. So L matching network. It has only two components. We will see about the T and pi matching networks, which have three components and gives you actually more degree of freedom. All right? So assume that we select two inductive components like XS and XL. Okay? One in parallel with RL and one in series with RS. L shape. Okay? Then I say that if I take this part as my ZL and take this part as my ZS, I should satisfy this condition to have a maximum power transferring from this to this network. I mean from this source to this network. And then this network, I know that this one does not consume any power. All the power is going to this one. Because this is reactive, it's not consumer. Okay? So if I write down the impedance of the ZL, this is the impedance of the ZL. So the RL in parallel with XL. And then the impedance of this is RS plus JXS, and the conjugate of that is RS minus JXS. Okay? So these two should be equal based on... Okay? To satisfy this condition, we just write down the element level. So expanding this equation, you can see that this is the expansion of the first one, and then if I want to divide it into two components, one of them is purely real and one of them is imaginary, because I want them to equalize these two parts, then we can write this equation like this. Okay? And then I equalize the real part and imaginary part. So in the real part, when we equalize, we see that the RS should be equal to this value, and then the XS should be equal to this value to satisfy the condition. We define the Q factor of R and L in parallel like this. And then we say that I replace the magnitude of R over XL as a Q here in these two equations. Then we find RS is RL divided by 1 plus Q squared, and XS is minus XLQ squared divided by 1 plus Q squared. Okay? So this is just a definition of the Q factor of R and L in parallel. So these two equations have answer if RL is greater than RS, because this number is always positive, and it ensures that the RS is less than RL. So this circuit that we have here is working only RL is greater than RS. Okay? For RL greater than RS, then we can find the value for the Q factor easily by this formula from here. I found it from here. So I found the Q factor, and then based on this Q factor, I can find the XL and XS, which is our goal. So we wanted to find the values for the XL and XS in such a way that this condition is satisfied. And I can find it. Based on this circuit, if we satisfy this condition, then we can say that the XL and XS are coming from these two. Please consider that the XS and XL always are opposite of each other. I mean, the sign is not the same. So if XL is inductor, then XS should be capacitor, and vice versa. So you cannot use inductor. So one of them is inductor, one of them is capacitor. Also, if we want to have a condition RL less than RS, I leave this to you. You can, again, draw this circuit. I mean, put these two components way around. Just move the position of these two. And then for RL less than RS, then this circuit is the answer. We call the first circuit as the down conversion circuit and the second circuit as the up conversion, because this one this one converts a higher resistance to a lower resistance, and this circuit converts a lower resistance to a higher resistance. So for example here, if again we have a RS of 50 ohm, then if we have RL 20 ohm, then we should use this circuit 2. The situation of selection of the XS and XL depends on what you want. Okay, if I want to first say that about the XL. So XL, if you put XL as inductor here, then definitely in low frequency, this circuit has a very high impedance, because this is going to short circuit here. And then in low frequency it has low impedance. Then it acts as a low pass filter. If you select XL as a capacitor, I just don't make a mistake. So if we have this circuit, so this is a low pass filter. high pass filter. And if we have this circuit, then this is a low pass filter. It depends on what we like. In the frequencies away from our resonance frequency. At the resonance frequency, they work, I mean, at the operating frequency that we define, they work perfect. But
then if we assume that XL is an inductor, then in the low frequency, that is the high pass filter.
L as inductor is high pass filter. Yes. Yeah. This is a high pass filter, and this is a low pass filter. Okay. So this is a method that we can convert a resistance into another resistance with just two elements, X and L, C and L. Okay? Is it clear? Okay. If it's clear, then we go to pi match. So sometimes we would like to have a kind of band pass filter performance. I mean, in the low pass filter, when you look at your matching network is like this. I mean, the performance of your matching network is like this, that it comes and then it goes down and then it comes and then it's like this. And this is your resonance frequency. So it drops suddenly after that. Okay? So this is for low pass filter. And then for the high pass filter, so it's again, it's like this. But sometimes we would like to have a kind of bandwidth and for more wideband designs. I mean, for example, I want to be like this, and then it goes down, and then somewhere else, for example, again it goes high. So I need that around my operating frequency, my circuit is working well, because it's a wideband design. It's not just for a single frequency. For example, I want to design a circuit which is working at 100 megahertz, and then the bandwidth is also plus minus 5 megahertz. So 10 megahertz around that, I would like to. So this circuit does not work because it drops suddenly after that. Also, this circuit maybe does not work. Okay? So for a band pass filter design, then we are going for pi match or X or T match. Then we say that for the case that we have a RL and RS, then we can design a pi match network with 3 elements. The shape is like pi, 3 reactive elements, and then we convert this to this one. To solve this solution, we use the same what we did in the previous slide. I just divide these 2 circuits. I mean, to find the values for the X1, X3, and X2, I divide this from here into 2 circuits. I mean, I try to match this RL for an imaginary value or resistance of R, and then by this circuit, and then I try to match this R to another, to RS by this circuit. I mean, I divide these two into two circuits and then follow the same instruction that we had in the previous one. And then at the end, so the value that I found here for the X3 is the same as what we found. The value that we found here is the same as what we found. And then the value for X2 is the addition of these two. I mean, it's X2A plus X2B.
How do we get the R?
You can select a number. The only condition that you have to consider is that this R should be both less than RL and less than RS. Why? Because this circuit is a kind of down conversion. I mean, the value of this R should be less than this RL. And this circuit is again an up conversion. So this R again should be less than RS. So if I want to send a power from a source with the impedance of 50 ohm to a load with the impedance of 100 ohm, the value of R should always be less than 50 ohm. It should be less than both of them. For these kind of exercises, we usually say that, okay, we need a bandwidth, and then based on this bandwidth, please design, for example, these elements in such a way that we can match these two resistors. So based on the bandwidths that you are receiving, you have to find the Q factor. So the Q factor, we say that is the Q factor is the RL divided by RS, for example, in this. And RL is our load, and RS is our R, the R that we assumed. So you should select the R in such a way that you satisfies the value for the Q factor. So this is how you should select R. Okay? So the criteria of selecting R is coming from this part. We will see in one example that how we should select the value for the R, and then based on the bandwidths that we need. Okay? And then definitely we have two Q factors, because this circuit has one Q factor and this circuit has another Q factor. But we should select the highest Q factor, because the highest Q factor has lowest bandwidth. So if the Q factor is like this, the bandwidth is smaller than if the Q factor is like this. Because bandwidth equals to F naught divided by Q factor. So the highest Q factor give you the lowest bandwidth. So we should select the highest Q factor. And the highest Q factor is coming from the maximum between RL and RS divided by R. Are you following me? Yeah.
So we just need to choose only one RL or a height one?
Yes, you have to select the highest RL or RS, and then equalize this to the Q factor, and then find the R, the value for the R. So any value of R less than that is working. You can select the R that you find from that one, but any value of R less than that is working. I mean, there is no a single answer for this question. It has lots of answers, but it has a range of numbers that you can select. Okay? Can I go to the next slide? The same thing we have for the T network. Again, T networks are working as bandpass filters. the same method. We just divide our circuit from this point. We have two circuits. I'm trying to use the circuit A again and circuit B to match my RS to a R and the RL to a R again. And then at the end, the X1 that I found is X1, the X3 that I found is the X3, and then the X2 is the parallel of X2A and X2B. In this situation, this circuit is up conversion circuit. So this R should be greater than RL. And this circuit is down conversion circuit. So this R should be greater than RS. Again, we should have R both greater than RL and RS. So the criteria of selecting R is the same. And again, to find the value for the R, we should consider the Q factor. And the Q factor here should be, again, the highest Q factor, because the highest Q factor gives you the minimum bandwidth, the lowest bandwidth. And then for highest Q factor, here we have to select the minimum of RL or RS to find the highest Q factor. So based on the bandwidth, you find the value for the R, and then based on this R, RL and RS, you can calculate the value for the X1, X2A, X3, and X2B, and then at the end, you do the X2A in parallel with X2B. Okay? So as an example, assume that we have a source with the impedance of 100 ohm and a load with the impedance of 50 ohm, and we want to match these two with a pi network. Our operating frequency is 100 megahertz, and then the bandwidth that we need is 5 megahertz. The 3 dB bandwidth that we need is 5 megahertz. Okay? So based on the center frequency or operating frequency or resonant frequency and the bandwidth, we can find the Q factor. Q factor equals to F naught divided by bandwidth. Okay? And it is 20. So we need a Q factor of 20 here. All right? And then based on Q factor of 20, we have to find the R. And we know that the Q factor equals to, in this down conversion circuit, is equals to maximum of RL and RS divided by R minus 1. So maximum of RL and RS is 100 ohm. 100 ohm divided by something, and assume that no minus 1. 100 ohm divided by something should be, a square root of that should be 20. So something should be 1 over 4. So the R then equals to 1 over 4. Oh. The square root of 400 is 20. Okay, so we find the R is, and then if we put this R, we find that the Q factor for the circuit 1 is 20 and for the circuit 2 is 14.1. Okay, so definitely this one ensures that the bandwidth is 5 megahertz, and this is the bandwidth is more than 5 megahertz. That's good. So for to find the values for X1 and X2A and X3 and X2B, you have to follow these two equations. So for the X1 and X3, you use this one, And then for the x2a and x2b, you use this equation. So x1 equals to rs divided by q, and x3 is rl divided by q. So x1 is 5, x3 is 3.50. Yeah. No. This circuit has the Q of 20. This circuit has the Q of 14.1. The Q is coming from RL over R or RS over R. The Q is not something that we can select. I mean, you have to calculate the Q, and then based on that Q, you find the value for X. So the Q for the upper one is RS over R minus 1 square root. And the Q for the lower one is RL over R minus 1. So the Q of this circuit and this circuit is different. The Q of this circuit is coming from the Q factor of these two elements in parallel, and the Q of this circuit is coming from these two elements.
Isn't the frequency and bandwidth the same?
The center frequency is the same, bandwidth is not the same. But definitely the bandwidth is more than 5 megahertz. The bandwidth of one of them is 5 megahertz, the bandwidth of the other one is more than 5 megahertz. You have to divide 100 by 14.1 to see that what's the bandwidth of this one. So the bandwidth of this one is coming from F divided by Q. 100 divided by 14 is around 7 something megahertz. And the bandwidth of this one is 5 megahertz. Then we ensure that the bandwidth of whole system is 5 megahertz. Okay? X1 is 5, X2a is minus 5, X3 is 3.55, and X2b is just
Why is X1 RS by Q?
from this formula. X1 is coming from,
RS by Q.
so in that circuit RL is RS. So in this circuit which one is RL? I mean, this is in parallel with this one, with this. In this circuit, this is in parallel. Assume that you just turn around this like that. Okay? Please consider that the sign of these two are different. Okay? If you find the sound the same, you made a mistake somewhere. And then,
Q of each is different, right?
yes,
The first one is all.
yes,
And the first, the most.
yes, the Q of this factor is 20, for example, and the Q factor of this is 14.1.
But for the upper feature, it's 20, right? In the upper segment.
Is
The high one.
less than 20. You will see from the number of this table that the bandwidth is slightly higher than 5 megahertz. If we draw this, you see that it's slightly higher than 5 megahertz. I mean, the combination of these two is definitely higher than 5 megahertz.
Then what is the Q equal to 20 that we have calculated from F naught by bandwidth in?
So we said that the minimum Q that we need is 5 megahertz. Okay.
Minimum bandwidth.
The minimum bandwidth that we need is 5 megahertz. So the minimum Q of this circuit should be 5 megahertz.
First.
Yeah, the minimum Q of this circuit should be 20.
Or for the high.
The whole
The whole.
should be 20, the minimum Q.
Is it the minimum Q or the maximum Q? Because for the
The maximum Q, sorry. The maximum Q should be 20.
There are two Qs. We select the bigger one, right?
You have to select the bigger one. I mentioned just here that you have to select the highest Q always. So the maximum Q is 20. So we have one Q which is 20, another Q which is 14. The combination of these two circuits gives you a Q factor, I don't know, 19, for example. But it is definitely less than 20. And the bandwidth is definitely higher than 5 megahertz. And then based on the operating frequency, which is 100 megahertz, if you replace it here, then you can find the value for the L1, for the C2, and for the L3. So for example, X1 is J omega L1, and we know the omega, and then you can find the L1. Please consider that in the pi network, you have to add the X2A and X2B, and in the T network, you have to put them in parallel. Omega is omega. Operating frequency. From this table, you see that this circuit, for example, at 70 megahertz, that the power that it delivers is near zero. And then it starts to increase, and then around 100 megahertz, it's around 100%. So it seems that the center frequency shifts a little bit, for example, from 100 megahertz, because in some point it is 1. Maybe it is, I don't know, 100.1 or 99.9. So we have to draw that. And then, again, it drops. And, for example, at 5 gigahertz, again, it starts to go up. So if we draw the HF, it's like this, that it goes up and then goes down, and then somewhere else again it starts to go up. To find out what's the bandwidth from this table, we just need to see that there is the half power. For example, half power is here. It's somewhere here between these two numbers, when it is 0.5. And then the half power here, which is between 100.02 and 100.03. So you see that the bandwidth is 5 megahertz. 2.5 higher than 100 megahertz, 2.5 lower than 100 megahertz. We have a half power from 97.5 to 102.5. Okay?
Shouldn't it be after 103?
No. It should be less than, yes, sorry. Yeah. Then definitely it is higher than 5 megahertz. And the center frequency shifts to higher than 100 megahertz. Thank you. Any question? So you can simulate this circuit. You should, I don't know, but if we simulate this circuit, what will happen in LCL? So LCL, then you can simply simulate it in the SPICE and see that what's the transfer function of the LCL in the LTS SPICE, and see that why it's going high again. Because usually LCL should have only one resonance or two resonances. When it goes high, it means that it has another resonance. Okay? Maybe it has two resonances. Good question. I can simulate this and tell you later next session.
By resonance, you mean a peak point and then it goes down somewhere?
Yeah. I mean that we have, you see that. So when we are going, for example, near 5 gigahertz, again, it goes high. So and maybe it has two poles. I don't know. Now I don't know what I can simulate it on the two. because maybe we need to write down this base like j omega L and j omega C, and then see that what happens in the denominator. Okay. For 1 L and C, definitely it has one resonance because it goes somewhere high and then drops, or it is dropping, goes high and then constant, almost constant. But for pi or T, maybe we have two resonances. Any other?
Can RS be anything like
All right, this is what I want to tell you. All right, so this is the case that we had for pure.
Yeah, so I know that Heinen-Morgenstern already proposed, but how do you decide where to use an inductor or where to use a capacitor in other circumstances?
You mean here?
Yes.
You mean that why we select, for example, we picked L.
Uh-huh.
You can pick C. No difference. If you select C, then this is definitely L and this is C.
Just assign it as one?
You can pick one. No difference. The behavior of these numbers are different. I mean that in this circuit, which is LCL, in low frequency it is 0. But when it is the CLC, definitely in lower frequency you have a pass band.
But here we say we just actually blending, right? So it doesn't constrain sign.
So here, if I tell you, you can select plus or minus, any of them. But when you select XL plus, then your XS is minus. If you select minus, then it's plus. It's on you. You can select another type of circuit. But then the behavior, apart from your working frequency, is different. So the behavior of this is a kind of high pass. I mean, in low frequency, with that L and with that C, you do not let the signal go through at DC. But when it is CLC, then definitely at DC, all the signal passes through. So in low frequency, it is good, and then maybe at your frequency, it's going high and then goes down. So the behavior is different. But at operating frequency and the bandwidths that you have, it works similar. Yeah.
So it really depends on what we have.
What you like.
High pass, high frequencies
Or low frequency, yeah.
And even a positive and negative sign assignment, if I assume that the capacitance is a positive sign, the inductor will be negative.
So when XL is positive, then it is inductor. When you select positive, means XL is inductor. When you select negative, means it's capacitor. Okay, so the question that your friends asked that, okay, what if it is not RS and RL? I mean, if it's not pure resistance, then what should we do? So assume that instead of RS we have this ZS, and then instead of RL we have this ZL, okay? And then I want to put, I'm doing this for a L network similar to pi or T. So this is the XS, this is the, for example, XL. So if I replace this ZS with a I don't know. For example, a resistor, if this ZS, okay, if this ZS equals to RS, actually this is not good that it's XS. If I mention this is, for example, X1 and this is X2. Okay. So if this RS equals to JXS, okay. If the XS is positive and XS is negative, so if it's positive, it means that it is inductor and it is capacitor. I mean, I can write this as this RS in parallel with a inductor, or I can write it as RS in parallel with a capacitor. So this is actually this circuit. The same thing here. I mean, this ZL, I can draw it as a parallel of RL and LL, or RL and CL. Okay? I mean, this ZL, again, this ZL equals to RL plus J XL. And then we can say that this XL, if it is positive, if XL is negative. If it is positive, it is capacitor. If negative, it's inductor, because it's in parallel. So then I can say that this is like this, or it is like this. So this is LL, RL, RL, CL. Okay. Again, I'm going to match this RS to this RL, and then the imaginary part, I mean the imaginary section of the source and the load, are inside of the matching network. Clear? No? If I assume that we have XS positive and XL positive, then I can redraw this circuit as plus minus, okay, XS is positive, then instead of ZS I can write down RS, and then this LS, and then this X1, and then this X2, positive, and then this CL and RL. I can take this now as X prime 1 and take these two as X prime 2 and solve the equation. Yeah. Yeah. You solve for matching RS to RL, and at the end when you find the value for the X prime 1 and X prime 2, you just remove this part, the part of, for example, which is belongs to the source and to the load. All good? Okay, if all good, then we can move to lecture 6, and then we have to finish the lecture 6 today because we are going to talk about the mixers and you need it for the next week lab. So I'm closing lecture 5 content and going to lecture 6. Okay, this lecture I'm going to talk about the LNAs first and then about the mixers. So I believe most of you have some at least basic knowledge on the LNAs and you've done something in the lab already. So we are going to cover the theories here and how we can design an LNA, a good LNA, and then going into the mixer, the different types of mixer, how we can combine two signals and what's the importance of these two components, which are almost available in all the RF circuits transceivers, transmitters. We have mixers, and in the receivers we have mixers and LNAs. So the first stage of each receiver in RF design is the LNA. Why? Because we know that from lecture 2 that the noise figure of a whole receiver is very dependent on the noise figure of the first stage. So the noise figure of the first stage should be low because the noise figure of the rest of the stages is going to be divided by the gain of the first stage, but the noise figure of the first stage is directly go to the noise figure of the total. Then we need to design an amplifier with high gain at the first stage, which does not show that much noise. Okay, so the contribution of the noise should be low, but the gain should be high. Also, it should be perfectly matched to the transmission line, because anything which is reflected at the first stage of your LNA, it means that you lose the power that you received from your antenna. And the transmission line, usually we say that, okay, the impedance is 50 ohm or 75 ohm, different. But usually we say that the impedance is pure resistive, okay? So we need to design an amplifier with a pure resistive input impedance to the transmission line that we select, which usually we say 50 ohm, okay? So the criteria that we compare the performance of two LNAs are these, that, okay, what's the gain of the LNA and what's the gain flatness. For example, I say that the gain of my LNA is 17 dB plus minus 0.2 or plus minus 1. So definitely the flatness is one of the criterion that we are interested, and also the gain itself. Then how much power it can tolerate. I mean the output power that it can deliver before it gets saturated, which we already see that we call this P1 dB. I mean, what will be the maximum output power before it gets saturated and the other harmonics comes up or power is reflected back, okay? And what is the noise figure of, for example, this LNA? How much noise this circuit is going to add to my received signal? We say that in the order of, for example, less than 2 dB, the LNA is a good one. 1.2, 1.3, 1.5. And then definitely the bandwidths. For example, we defined an LNA, it's working at 1 gigahertz, the bandwidth is 10 megahertz. Or we define an LNA which is working, for example, from 2 to 18 gigahertz. So the bandwidths could be different. The amount of the power that we consume to bias our circuit. So this is the DC power. DC power that we use. I mean the voltage of biasing multiplied by the current that we consume to bias our circuit. So if in the exam I ask that, okay, what's the power dissipated in this circuit, then you have to look at the VCC and ICC and just times these two. Okay? So the power that we consume. And then definitely the VSWR, input matching, output matching, how good they are, and it shows that how much power we can transmit from the input of the LNA to the output. There are, okay, so this is the overall, so this black diagram here is the overall approach that we will have. So we are designing an LNA. First we bias it, and then we design two input and output matching network. It comes from the power coming from the RF source or from an antenna, and then it goes to a load or next stage or a mixer or any other circuit. Okay. So 3 steps we are going to follow. First, how we can bias a transistor, which I believe you know from the analog electronic. Then how we can isolate the DC and AC paths, and then how we can match a LNA. So the matching for the LNA could be a bit different because we need a pure resistive, and we will see that. Okay. So first of all, the biasing circuits. From the basic analog electronics, we know that we have 2 types of biasing: the passive biasing or active biasing, which we call it current mirror. Okay. So in the passive biasing, if you have a transistor like this, a BJT like this, and this is your input, this is your output, then you need to bias the base, and you need to bias the collector. So bias. We need to bias the base for this diode, and then we need to bias the collector for this diode. In the passive biasing, we usually use resistors. Okay, resistors are very simple. You can easily find the voltage at Vref by dividing the voltage divider based on these 2 resistors. And then, for example, if you need, 0.7 volt to bias the base of this, you just put this 0.7 and then find the values for the R1 and R2. Pick a number for the current and then find R1 and R2. We will see in the few slides later. The problem with the resistor biasing is that it is dependent on the temperature. I mean, by changing the temperature, then the amount of noise is changing. By changing the temperature, the current is changing, and then the performance of your amplifier is changing. So the main disadvantage, if I want to say, that it is sensitive to the change of the temperature, and it has poor temperature stability. So to increase the stability, you can put a capacitor here to just denoise the circuit. So this is what we usually do. So if we want to have a better Vref here, then by just putting a capacitor here, we can stabilize the voltage at this point. And then we can use a combination of R L and C to isolate between the RF and DC sources, which we will see in the next slide. In the active biasing, we use another transistor exactly. It could be similar to the Q1. I mean, we can select Q2 exactly similar to Q1, or it could be different. I mean, it depends. Because usually we can say this in two terms. If we select these two, then the design is much easier. And also they are thermally coupled. We say that they are because the characteristic of this transistor and this transistor are the same. When by changing the temperature, it is changed. This one changing the same in the same manner. It's changing. The second one is changing. Okay. But the problem is that the transistor that we usually use for the RF transistor is an expensive transistor. So then, if we use Q2 exactly similar to Q1, and we just want to use this Q2 as a current source, it does not do anything else for us, then we are actually making the price of our circuit double. Okay? So these are the two things that you need to consider. But also the size of this circuit is bigger. I mean, this circuit occupies more areas on your circuit board instead of only two small resistors. Anyway, it is more stable on temperature, but it is more complex, and it consumes also more power. So is there anyone who is not familiar with the current mirror? Current mirror. So in the current mirror circuit, we use one transistor to bias another transistor, and then we say that as the IB here for these two are the same, any current passes through this transistor is exactly passing through this transistor. So the IC2. Then we try to bias the second one. It could be like this, and then exactly the current that we get here, we say that that current is going through the other one. So this is a current source, I mean here, not this one. This is, we can say, is a current source, and then exactly the same current we have in the. You can select a number for these. We will see that how we are going to do the active biasing. You can select a number, for example, for this IB, and then based on this IB, you have to find the value for this one, and then find the values for the R1 and R2 and R3. So this R3 is not necessary. If we have an impedance here, it's better to put that impedance here as well. If we don't have, then we don't need to. Similar.
I both side is approximate to be the same height.
Sorry?
I at both sides, I this direction and this direction.
Yeah.
Approximate to be the same.
Yeah. We will see in the example that how what are the relations. Sorry. Yeah. Yeah, this one is the, actually this part is the current source. We can say that this is the current source. It's acting as a current source. It's acting as a current source. Yep. Like here. I will solve one example. You will see that. So in a passive biasing, for example, we have two examples here. We want to bias the transistor Q1 and Q2. So two different biasing methods. For the first one, we use 2 resistors, and for the second one, we use 4 resistors. So a kind of in the first one, we use the R1 shared between the collector and the base, but for the second one, they are different. We use R4 to bias the collector and use the R1, R2, and R3 to bias the base. Okay? In the first one, if we look at the current I1, so we see that this I1 is the addition of this current and this current, okay, which is IC and IB. And this IC and IB has the relation of IC equals to beta IB. And then you can see that this I1 is this one. Then, if we, in all these applications, we know that what's the value for the IC. I mean, the value for the IC is given. For example, they say that I want to bias a transistor that has a collector current of 10 milliampere. So IC is given, and also the voltage at the collector is given. And what's the value for the VCE? So usually what we apply for the VCE, I mean, what is the optimum value for the VCE? VCE, not VB, VCE. Why 2.5? Okay, VCC divided by 2. Why? Because when we bias our transistor at this point, then we have the maximum degree of freedom for the RF signal. So if you look at the, so this is voltage, this is time. Then if our DC is like this and our RF is like this on top of that, then if it is 2.5, we have the, or VCC divided by 2, it has the maximum degree of freedom before reaching to the ground or reaching to the VCC to get saturated. Yes. You have to, definitely we have to go to the triode or saturation for the CMOS or BJT, but the number that we select for the VCE should be at the point that it has the maximum swing. So you have a biasing point, and we say that this is the DC VCE. And then your RF signal is going to come on top of this. So RF signal is AC. And then when it reaches to the ground, or it reaches to the VCC, it gets clipped. So to have a maximum output, and this is actually the P1 dB. So before reaching that point that it gets clipped, then it's better to bias your transistor in the middle. Okay. Anyway, it is given. If it's not given, then you have to assume the best one. And it's for this circuit, because this circuit does not have anything here. If it has something here, then it's different. Okay. So the IC and VC is given, and we know that what's the value for the, so to find the value for the R1, because we know the value for the I1 is beta plus 1 divided by beta IC, and beta is also given, is a parameter from the transistor. You know what's the value for the I1. You can easily calculate the R1 by this equation, and then you can calculate the R2 by this equation. And VBE should be greater than the voltage threshold of the transistor. If the voltage threshold is 0.6, 0.7, 0.8, then you need to replace it here. This is very simple. For this configuration, you have more degree of freedom, because if we want to find the voltage at this Vx, we can, because we have a resistor here. If we don't have a resistor here, then this Vx is exactly VBE. Okay? But as we have another resistor here, then we can pick a number for the Vx. Okay? So we pick a number for the Vx, and then assume a current ratio between the current which is passing through this line and the current of IB. I mean, if we assume the current which is passing, this line is IX, and the current which is going to the base of this transistor is IB. For example, I assume that IX is 10 IB, and pick a number for Vx, number that we want. So the Vx definitely should be greater than the VBE. For example, if VBE is 0.7, then we select Vx, for example, 2 volt. So this point is VBE, and to bias this transistor, of course VBE should be greater than V threshold. Okay? And to current going through this way, then the Vx should be also greater than VBE. So if V threshold, for example, if V threshold is 0.7, then we can say that VBE 0.7, and then Vx, for example, 2 volt. You know the Vx, you know the VBE, we know the IB. Why we know the IB? Because we know IC and beta. You can find easily the RC. And R1 also is based on the Vx and Ix we can find. R2. So R2, actually the current is passing through here is Ix plus IB, which is 11 IB, for example, in this case. And then we know the VCC and Vx. And then this R4 exactly coming from the way that we calculated for here. So in this circuit we have this RF choke and this RF choke, this AC blocking and this AC blocking. In this circuit the same. We have RF choke and RF choke, AC blocking capacitor and AC blocking capacitor. These 4 elements helps us to just isolate our DC path from our RF path. I mean, this RF chuck and this capacitor does not let the RF signal go to the VCC and then distribute in the rest of your circuit. Again here. So the RF in that I apply here and the RF out that I get from here, with the help of this network and this network, is going to get isolated from the DC path. How we select these numbers? So in our operating frequency, the values for this j omega L should be high, in the order of kilo ohm. And the value for this capacitor should be almost short, in the order of ohm. I mean, I'm going to short this point in the RF. Okay? So this is AC blocking, this is AC blocking, and the same for this. Both of them are blocked AC signal.
To remove the equivalent from AC to DC or from DC to...
So in the DC, actually this RF chuck assume that it has a impedance of inductance of L. Then the ZL equals to j omega L. Okay, so this j omega L, if omega equals to 0, then it is almost 0. And this omega L, this ZL, if omega equals to omega naught, which is our operating frequency, it is, I mean, ZL is omega L. And then this omega L should be few kilo ohms, 10 kilo ohms, 2 kilo ohms, something like that. You can do, but I told you just in the previous slide that this C helps you for the stability, temperature stability. Here. Okay. With L is enough, but usually we use a capacitor there. The reason that we use AC blocking, because we do not want that this AC signal is going to the power supply and then go to the, for example, the circuit, the neighbor circuit, to your processor, to your memory. Okay. Also to the other RF circuits, because it seems that then you have a loop and you have a feedback, and then it has a high chance of resonation. Okay. No, not a break time. Just I follow this active biasing, and then we can have a break. So in the active biasing, I said that we use transistor Q1 as a current mirror of this Q2, and then I try to bias this Q1, and then the same current is passing through this. So the idea for the active biasing is that we would like to minimize the performance of our circuit to beta fluctuations. So if the beta is changing, which is changing in the process, for example, you buy two transistor, two NPN, 2N22 transistor, and it says that the beta is, I don't know, 200. And when you put one of them in the circuit, you get one number, and then when you put another, for example, the first one shows a beta of 190, the second one shows a beta of 220. So we would like to bias this circuit that it has the lowest dependency on the beta fluctuations, because beta is not something which we can control. it's difficult in the process. If we look at the current which is passing through the collector here, IC2, we can say this IC2 equals to the beta IB2, and the beta IB2 actually is the voltage at this point minus the voltage at this point divided by this resistor. So the voltage VC1 and the VBE divided by RB. Again, in this, we know that what's the value for the VBE, we know the value for the IC, and we know the value for beta and VC. These four are known. And then the VC1, so the voltage that we have here, the VC1 is so R Thevenin and V Thevenin. So V Thevenin I don't know what did I do here. RC1 and RV2. So these two. Okay, maybe we can have a break. We can have a break and we continue on 4:40 because I don't know what I do.
For the assignment, in the first part, we have to solve it using the method that you've told in the lectures, right? Assuming them to be resistors 1 by GM and okay.
Yep.
And same for the MOSFET, right?
Yep.
Use
Yep.
them as resistors.
Yep.
Is it correct?
I don't know the answers.
But the method is.
Yeah.
Perfect.
Yeah.
I think thank you. Question two.
Because like there's a current source going from this way, right?
Yep.
And then I have to multiply with the impedance of C1 in order to find the voltage V out. But the thing is, like I don't know, like the operating frequency in order to find the resistance impedance of.
So actually, this is the heart of the question. I mean, this is what you should find. So the operating frequency is DC to infinity.
Sorry?
This to infinity. I mean, this circuit is working from in all the frequencies, but it has a gain bandwidth which damps the frequency, the upper frequency, and then you have to
But
find.
I got bandwidth, right? But it's still bandwidth, so I can just choose any frequency in that bandwidth as a total frequency.
True, but so we said that the Vn, I mean the S out of a network is equals to integral of the S in HF squared.
Sorry, H.
HF is the transfer function of this. So you have a transfer function of this, and then it is.
But this one is not a like the transfer function here is just a constant.
But then you should do the integral.
The integral.
True, but it seems that your load is frequency dependent.
Yeah, because
Just write down the integral and see that what it happens. Instead of just multiply those two.
yeah, but I got the transfer function with one. It's just like
Transfer function is constant, correct? It's a gain.
yeah, but like, and then I did an integral from frequency from 0 to f0 to f0 plus some bandwidth.
How can I write it this?
And this one is a constant, you can just move it out.
Yeah, but this Sin is not constant.
But S in here for the B.
For example, if it is the voltage, then when you put it, pass it into a capacitor, then it's frequency dependent. Okay, I have to figure this out. I got lost.
Ask some question.
Yeah.
Okay, that was the first lecture. Here, if we look to the I stage, it's like the 1 over GM parallel with the RO. I want to ask, I think this one is just a RO. So which RO for this one? Is the R output resistor for this transistor,
Transistor. Yeah.
or this transistor, or the
No,
down
this
transistor? Just this transistor. So what about the 1 over GM? What is that? Where is it come from? I think it's the resistor.
Yeah.
VG is the GM of times VBS, and then VB is 0, and the VBS is equal to negative V test. So you got like so this branch is like 1 over GM, and then the other branch is RO. So when you look up, it's like it's 1 over GM parallel with the RO. When you look into the space.
Just one question. You said, because when we were considering pure resistance, resistive, RSS pure resistive and RLS pure resistive. Then we said that if XL is positive, then we assume it's an inductor, and if it's XL is negative, it's a capacitor. But when we are not considering it as pure resistive, then it's like contradicting.
No,
No?
for this one. So for example, assume that instead of RS, we have a ZS. It's not a pure resistive. So it is a combination of, for example, a resistor and inductor or resistor and capacitor. So then this part, I can say that, okay, we have a pure resistive, and then this part is going to add to this one. For the other one, the same. So the inductor or capacitor in parallel, you have.
It's just the sign thing. Then we are assuming that x is greater than 0 means it's inductive, right? It's an inductor connected.
Yeah.
Then XL greater than 0, shouldn't it be an inductor as well? Because we said that
In parallel of these two. Write this in parallel and find the R for this, and then you will see that then the total, then this one is positive because it's 1 over j omega, and then it comes to the magnitude. Okay. All right, guys, can we continue? Actually, I didn't understand that what's going on here because I didn't find to check. All right, so from here to here, I don't understand. Frankly speaking, I don't understand. And I didn't find to check because your friends are coming and asking questions, so I didn't check. But I can leave it to you. Okay? Maybe you understand and tell me as well. And I will discuss this next session. The only thing that I want to say is that, okay, we said that we want to minimize the beta dependence of the performance. So to minimize that, when we find the relation of IC2 based on all these values, based on this, when you replace all these, and you see that the equation for the IC2 is this equation. I mean, it's following. And then to find that what is the condition that we received the minimum dependency on the beta fluctuations, we just need to run this differential equation. And based on that, we can find that the RC1 should be RB1 divided by 2 beta naught. So this is the condition that we can find from here. If you do the differentiation. And then based on these, you can find the values for the RB1. Again, we have to assume that this IC1 is 10 times, this is the degree of freedom that we have. So we assume this, and we find the RB2 and the RC2. So 4 design parameters that we need to find. Go through this. I think it should be fine, but now I don't know.
Excuse me.
Yeah.
VTNet is the Thevenin's voltage, right? Like VCC is opposite voltage by opposite resistance by sum of resistance. That This is how the VTH comes.
Oh, okay, can I have one question? Whereas the VTH in this case, it usually is open circuit voltage, right? And what is
Yes.
where is supposed to be the open part that we look through inside?
So the R Thevenin is the Thevenin between these two.
Yeah.
Yeah, and the potential of VTH.
Open circuit between the.
With that.
Minus RTH IC1.
Yeah.
So this is the IC1
Yeah. This.
multiplied by this R Thevenin. So Thevenin voltage. Good question. Actually. You know that there is Thevenin voltage, then maybe the problem is that. Okay, Thevenin voltage. Load to this transistor. I don't know. Let's move on. Okay. We will discuss it later. All right. So okay, in a bipolar transistor, if we find that we have a assume that we have a impedance ZE in the emitter part of a bipolar transistor. Okay, if we write down the small signal model for this, and this can come from, for example, the packaging, the pads, the LC that we have. So all these, when you make a transistor in a chip, then all these parasitics are coming. So easily we can have a load in the emitter of our transistor, and this could be out of control. I mean, I myself did not put that. It's coming from the package or from the pad. Okay. Let's see what will happen when we have this kind of impedances in the transistor emitter. So if we have this ZE, and I want to see that what is the effect of this on my transconductance or the gain of my transistor, we see that at the voltage at point Vx is actually the voltage, the current passing through this line multiplied by Ze. And I call this IE. And I know that this IE is the addition of these two currents, the current from this path and this path. Sorry. Yeah. We can say beta plus 1 divided by beta, then I out. And as beta is high, then we can say 1 I out. Okay? So it is, we can say that it is almost I out by ZE, so the voltage at this point. And then we define the transconductance of a transistor as I out divided by V in. And based on this equation, you can find that the transconductance, the new transconductance is the original transconductance divided by 1 plus GMZ. Okay? This part is VBE. So what we can see here is that to adjust the gain of a transistor, then we can add a ZE in such a way that the dependency of the gain of the transistor to GM reduces. Why? Because GM is related to IC. Okay. And then this IC related to temperature. It means that by changing the temperature, for example, you design an amplifier, it works very good at 20 degrees, then you are going and install it in a radar in the middle of nowhere, and then it is 50 degrees, or it is minus 40 degrees. You assume that your amplifier gives you a gain of, I don't know, 15 dB, and then it gives you a gain of 12 dB. Then by that, you can detect objects, for example, in a half distance from your radar. So to decrease the dependency of the gain of your amplifier to the temperature, we can add a ZE, and then you see that the dependence is reduced by 1 plus GMZE. This is the impression. So what will happen to the input impedance of this transistor if I add a ZE here? So if I add assume that we have an inductor. So this inductor is coming from the package I told you. So if we have an inductor here, then the current which is passing through this inductor is beta plus 1 IB. Then if I want to move it into the base, I can say that, okay, it seems that this inductor, I can replace it by another inductor, and the value of this inductor is beta 1 multiplied by LB. The same thing we have when we have something in the base of a transistor, and we want to see the effect of that in the emitter, then you need to divide it by beta plus 1. Then the new small signal model for our transistor will be, so this is your transistor, actually the original transistor, and then I move this L from the emitter side into the base, and then say that the value is beta plus 1 LP. Okay? And this RB also is the resistance of the input resistance that we have for the track or for the pad or something. The value is very low. So to do the matching for a bipolar transistor, LNA transistor, then we have to match this Z in to the source. Okay. The next is the effect of the L in the CMOS transistor, and it's very interesting actually. I mean, it helps you a lot to do the matching. So if we have a CMOS and then we put a L inside here, inside the source terminal, so the small signal model is like this. So we know that the input resistance of a CMOS is infinity, and the input port we can just model with the capacitor CGS. We have this LS in the emitter, in the source, and then this is the current which is coming. So the voltage in, we can say that this voltage is the current which passing through this one plus the current which passing through this one, the voltage in. So the current which passing through the CGS is I in, so this is the voltage VGS, and the current which passing through this is the I in plus GMVGS. Okay? And then to find the V in divided by I in, you can easily say that also VGS here equals to I in divided by SCGS, so here. And then you can simply find the input impedance of this transistor. The interesting part of this is that when we move this LS, I mean the effect of this LS in the input impedance of this transistor, it shows two elements. One, so this is the original 1 over SCGS that we had. This is the LS which goes into the gate terminal, and this is the another component which it generates, and you see that the materials of this component is resistive. I mean, 1L can generate L and R here. So now the Z in equals to 1L in series with 1C with series in 1R. It is very important in LNA design, because in LNA design to do the matching we don't want to use R, but it seems that we put a L and it shows a resistance in the input. So it makes our work much easier, because by selecting this R equals to RS and then select these two numbers in such a way that it is going to resonate in our operating frequency, then the matching is done. So the input impedance, this is what we just found. I just add another inductor. I mean, comparing to the previous one, I just add another inductor, LG, and then we say that the input impedance is the contribution of the CGS, the contribution of the LG and LS, and again the contribution of the LS that moves to the gate. So if I want to match this impedance with a source of Rs, then it's easily, I should put this equals to Rs, so the resistance part should be the same, and then these two also should resonate at our operating frequency. Then, by selecting this LS, I can match the real part, and then by selecting this LG, which is a contribution to this L total, then I can run at the desired operating frequency. I mean, my circuit is resonating at this frequency with the help of this LS to find equal to RS, and to this LT, and this LT equals to LG plus LS. So LS I know, and then we need to find the LT. And then we say that, okay, this circuit is matched at this omega optimum or omega naught, or omega resonance. Okay? So I did the matching, and also I reduced the gain dependency on the GM with just adding one L in the source of the transistor. We call this L as a degeneration or degenerative impedance or inductance. So if we look at this circuit here, we see that we have an R, L, and C in series. And I just mentioned at the beginning of this session that the Q for RLC in series equals to 1 over omega RC. Okay? So if you look into this circuit, I mean, if you just draw this part of the circuit, you see that we have a RS, we have a L total, and this L total is LG plus LS. We have a GM LS divided by CGS, and then we have a capacitor CGS. And then the Q factor for this circuit is 1 over omega RC. What is R? Plus RS. And these two are equal. We know that these two are equal. So the R is 2RS, and the C is CGS, and omega is omega. So this is the Q factor. If you look at the GM, actually GM is I out divided by V in. And this I out divided by V in, I can say that I out divided by VGS, which is GM, a small GM, and VGS divided by V in. So what is the VGS? So this is the VGS. So this is G, this is S. So VGS is the voltage across this capacitor. What is the VGS over V in? Is the impedance of this part divided by the impedance of the whole. I mean, it is CGS divided by whole of this. So these two are cancelling each other at the resonant frequency, I mean the L and C, and the impedance of this whole chain is only 2RS. And we see that it is GMQ. So the Q factor of the matching circuit actually shows the gain of your transistor, the transconductance gain of your transistor. Is it clear? Is it clear that why VGS over V in is only this one? R L R C plus minus VGS V in RS. This one is also RS from here, and this LS and CGS. So LS and CGS are neutralizing each other at the resonant frequency, because the resonant frequency we have this, which is this LT. Okay, so the voltage across this is VGS, and it is equal to the V in multiplied by the just impedance divider. Impedance divider CGS divided by 1 divided by 2 RS. Yeah. So if you see, we put two transistors here. So the transistor 1 is actually your main transistor, and the transistor 2, we call this configuration as a cascade. Cascade configuration. So cascade configuration actually shows a better isolation from output to the input. Why? Because if you remember from the lecture 1, the model for the transistor that we had is like this, that we had a CGS and then another capacitor here and then the current. So this is your drain, this is your source, this is your gate, and then this is CGD, and this is your CGS. Okay, and this is the current GM VGS. Okay, so because of this capacitor, then we have a feedback from output to input, and this is what we don't like. We want LNA to be a one-directional network. I mean, I would like that the S21 for this is high and S12 is very low. I don't want the signal goes from the output to the input, because if the signal goes from output to the input, then it has a feedback, and then my circuit has a chance of being unstable and oscillating instead of amplifying. Then we put another transistor, and then we increase the isolation based on this. What's the effect of this transistor on the gain? The transistor M2 on the gain? No, I get output from here, not here.
So we are given that the gain at transistor 2 and the gain in transistor 1, and then.
Okay, so the gain of the transistor 1 is big GM. What's the gain of the transistor 2? Any clue? Hossein?
From the output of M1.
So this is in, this is out.
It's common to, it should be, no, it should be GM or
GM are out.
R out is
It's common gate. It's not common emitter. Is GM are out.
yeah, it's positive.
It's just a switch. It's a FET switch. You turn this on. It's going from here to here. The gain of this is 1. It's working in saturation. It's switch. You just connect it to the VCC. It's always on. anything is going here, any current is going here, the same is going there. The gain is 1. So it does not have any effect on the gain, but it gives you isolation. So the S21 does not change, but the S12 is increasing. S12 is decreasing. All right, so this is the complete CMOS element. If we go for the BJT, okay, and then in the output, you see that we put a RLC in parallel. This is what I mentioned in the beginning of this session, that again, we should select the value for the L and for the C in such a way that it is resonating at the frequency of interest based on the Q factor that you want. The bandwidth, for example, they said that, okay, we want 10 megahertz bandwidth at 200 megahertz. You know the Q factor, and then you should select the L and C. You know the omega, and you know the Q factor. Easily you can select the L and C. And this is do the output matching for you. So the input matching we did with the selection of this LG and LS, and the output matching we have to do with the L out and C out. Okay? I will give you one question on this in the assignment 2. In the assignment. Okay? Not in the exam. To solve this and also simulate it to see that.
So in that we look from the source to the M2 is infinity, right?
Two
That we look
here.
from the source of M2 no, from the source from the IN direction here to M2 is infinity, right? Otherwise the voltage will drop and we can't occupy it.
It's just a FET. It's just a switch like this. I mean, you have a
So
switch.
if you calculate the transistor and then if the input resistance is not that high, then you can't multiply.
What is the working region of this one? Is it in saturation? It is in triode? It is in linear? It's in cutoff? Because this is, I mean, this this VGS is higher than VGS minus V threshold is higher than VDS. So it is in saturation region.
It's working as switch, but instead you have more gains because you have C2.
It does not have any gain. It doesn't give you gain. Gain is 1. So the gain of this is 1.
But no gain in current, gain in voltage. I mean, from the
No difference. It's a common gate. What he said, it's a common gate. Look at the basic electronic, what is the gain of a common gate? It's when it is biasing in the saturation. Okay, for a BJT. For a BJT, again, we put it in a cascode, and then I use one L here, which is LS, and then I get the output from this point. This is V out. I add inductor here, VCC, I bias this, and then I said that I apply my, so I have a biasing here to bias the base of this, and then again we have a source with RS, and then here you need a matching network. So again here, to isolate the biasing from your DC power supply, we use the RF chuck, here also we use the RF chuck. To find this matching network, it's not as straightforward as the CMOS, because here what you see as a Z-in, so Z-in, you saw that Z-in equals to this R pi in parallel with C pi plus beta plus 1 multiplied by LS. Okay. So the resistive value of this Z-in is not controllable. So definitely you need a matching network. You need an LC matching network. No, I mean that from this point, if you look, this Z-in is this value. So the resistance of this Z-in is not RS. You cannot control that to RS. So definitely we need a matching network similar to what I said. We have one R, we have another R, and we need L match, P match, or T match here. We cannot simply match it with a single LG. Okay? It needs L match, or at least L match. Again, we use two transistors. This transistor Q2 is for increasing the isolation. So one thing that I want to mention here is that if we want to block the DC, I want to block this DC going to the previous stage and block this DC to going to the next stage. Why I would like that? Because I don't want to next stage or previous stage DC is affecting the biasing conditions of my stage. And I don't want that my stage affecting their stage. So I would like to block DC going to the other stage. Then you can simply put a capacitor here. You can simply put a capacitor here, and then this is the DC blocking capacitor. The same here. And this is again the DC blocking capacitor. The value of this DC blocking capacitor, again, at the DC should be very high, and at your operating frequency should be very low. So the value of the ZCB equals to 1 over J omega CB at omega equals to 0 should be infinity, and at omega equals to omega naught should be very small, for example less than 1 ohm. Okay. Is it clear? Okay. If we look at an example, assume that we have a transistor, we want to work at 1.5 gigahertz. Okay? So the frequency of operation is given, the W and L and C oxide and mu n is given. These are the transistors and the transistors parameters. What's the width and length of the channel, what's the capacitance of the gate, and also the mobility of the N, the mobility of the electrons. And then we say that I want that this transistor is biased at 5 milliampere. Then you can simply find the GM as it is working in the saturation, then GM is coming from here. So GM is 2 milliamp divided by volt. So this equation is maybe is new for you, but this is the capacitance, the effective capacitance of a gate. So effective capacitance of the gate is the area of the gate, which is W multiplied by L divided by multiplied by the capacitance per unit, 2/3. This is the formula that we have. Then we can find what's the value for CGS. From those equations, we know that
CGS is the effective capacitance.
the effective, I mean the capacitance. So usually, if we don't have effective, we don't have this 2/3. It is Cox multiplied WL. But we say that effectively it is 2/3 times of that. Then, from the formula that I told you, first we define the LS, because we know that what's the GM, what's the CGS, and then what the RS 50 ohm. You can easily find the LS, the value that we have to put here. And then from the operating frequency, we know that this LT also is LS plus LG. Then we find the value for LG, and it is 20 nanohenry. So we put a 20 nanohenry here, a 1.4 nanohenry here, and then it is matched to the 50. Are you tired? No? Okay, good. So any question? Yeah.
Just that configuration, we keep what
Just louder, sorry.
sorry, the configuration there, all our designs will be around that configuration, right? We don't have any. We say like amplifier design will be exactly that configuration.
So this configuration, actually you see that we used active biasing here. So the good things, that the advantage of this design, I can say that it is active biasing, and you see that the transistor that we use for the active biasing is different from the transistor that we use for the RF. So this transistor is a bigger one, maybe cheaper. But these two transistors, I mean the transistors in the RF part, the same. So both of them are the same. This is the DC blocking capacitor. This L and this C is resonating at your frequency and going to match the output. Also, this L is a AC blocking L. Okay. So here actually we didn't put AC blocking, but this resistor is very big. I mean, it's already in the order of kilo ohm. So it is block the AC signal going through the DC part. What the novelty of this, I mean the advantage of this is that with only one component you can match. We usually need two components to match. But when we put a degeneration or degenerative impedance here and actually inductance here, then you can match the CMOS with only one component, because the difference between this and the BJT is that this input impedance of this is infinite, but the input impedance of the BJT is R pi. It's not infinite, and because of that, for that you need a matching network, L matching or pi matching network. But most of the LNAs are using a cascode design or a multiple stage of cascode design.
inductor LD is actually the AC blockade.
The inductor,
LD, which is 7 nanometer.
yes, and also it acts as a resonance, I mean the RLC of the output with this C, this L and this C are resonating.
It's in the output, connected to the output.
Yeah, you have to select this value for the CL, that's the value for the CL, and then it should resonate as F1. Clear? Okay. So if clear, we are going to next the mixers. So mixers, okay, the usage of mixers are more than LNAs because mixers we use in the transmitters and receivers both, especially in the wireless communication or in the radars. We use mixers to up convert in the transmitter and then down convert in the receivers. In most of the wireless communication systems, we use, for example, 2 mixers for IQ in transmitter and 2 mixers in the receivers. But the block diagram I already put in the lecture 1 slide. Okay. What I mentioned in previous lectures, that if a system has one input and one output, and then the input has a component of F1, only component of F1. Then if we want that output has components other than F1, then we have 2 choices. One, this system is be nonlinear, or this system be time variant. So these are the 2 conditions that we have. I mean that if a system is linear and time invariant, it cannot generate output element which is not available in the input. So this system either should be, for example, LTV or should be nonlinear. If we want that the frequency of output and input are different, or a combination of the input frequency and some other frequencies. So this is what we already mentioned. So what does mixer do? Mixer is a kind of multiplier. I mean, assume that we have a multiplier and it has a RF signal, LO signal, and IF signal. I draw this in 3-port network, but it could be 2-port. I mean, these 2 could come from 1 port. RF and LO come from 1 port, and the IF is the output. So definitely this is output, and these 2 could come from a single port or from individual ports. Okay? And then we say that this IF is RF multiplied by LO. This is what a mixer does. How we can implement this in electronics, we will see that if we have a signal X1 and X2, and this X1, for example, is your RF signal and X2 is your LO signal, then the multiplication of these 2 shows 2 components at different frequencies. So we have one input. For example, assume that we have an input RF, okay, and LO is inside the system. I mean, it's inside the system. So we have the input RF, only one input, and this is inside the system. Then in the input we have only frequency omega 1, but in the output we have another frequencies. So this system could be nonlinear or LTV. If this LO is inside the system, it could be linear, but it is LTV because it's changing by time. The characteristics of the system is changing by time. And you see that the multiplication results with the sum and different frequencies of the inputs. And the amplitude is proportional to the amplitude of these two, RF and LO. Then we say that if we assume that this LO amplitude is constant, because LO is something that we are generating in our receiver, so it's not dependent on the input signal. RF is something that we get from the antenna. LO is something that we are generating in our system to, for example, down convert or up convert. So if we assume that this LO that we are generating is constant, I mean this B is constant, then the output is proportional directly to the input. So this, the amplitude is transferring to the IF direct. And then we define a parameter with the name of conversion gain, and then we say that this conversion gain is the ratio between the IF amplitude and RF amplitude. I mean how much signal I send to this mixer, and then the result that I get in the output, what's the ratio between the amplitude of these two. So conversion gain equal to amplitude of RF, amplitude of IF divided by amplitude of RF. For example, in this simple circuit, then the conversion, then it's B over 2. It seems that the conversion gain is dependent on the value of the LO. And then we define S-pores. So S-pore is those that we don't like in the output. So if a mixer has an input of frequency omega 1 and the LO of omega 2, then in the output, in addition to these two, we will see all these frequencies as well. We can't see. And then we call them the unwanted signals or unwanted components or unwanted elements, and we call them S-pores. So we need to get rid of this. So as I said, we can do the mixing in two ways. One with a nonlinear system, and one with a linear but time-varying system. So nonlinear system, if we say that the function of a nonlinear system we can write as this. This is what we can say from the Taylor, or from the series expansion of a nonlinear system. So any nonlinear system can be modeled by this. And then I said that we can have a 2 ports, and then I put this V in as a combination of the LO plus RF. I mean, I applied both of the signals into the port 1, and then look at the output. And this is our output IF. Okay. Then, in general, we can see that in the output we have 3 types of signals, the DC terms, the harmonics, and then the intermodulations. These DC terms coming from the even order components, and then we can just filter it with a single capacitor. We can stop here, and I think you need to have a look at these lecture slides on the mixers before going to the lab. But in the lab, actually, you don't need that much of the concept and different types of the mixers. But what you are going to measure is what we covered in the lecture 3. You need to measure the IP3, P1 dB, and then the harmonics. So the harmonics that I just mentioned, that for example, if we have omega 1 and omega 2 at the input, then we are interested in omega 1 minus omega 2 and omega 1 plus omega 2. Depends on it is in the transmitter or in the receiver. So in transmitter, we are going to doing the up convert, omega 1 plus omega 2 is the desired signal. In the receiver, we are down converting, and omega 1 minus omega 2. And then you are going to see that what's the value for the IP3, what's the value for the P1 dB of the mixer, and then the nonlinearities and the spoors. So these are the concepts that I already mentioned. But please have a look. From here, actually you don't need in the lab, but before here you need to know at least what's the conversion gain. These are the parameters that you need to follow. Any question up to this point? If not, we can have a fast quiz. So could you please log into the Mars? Okay. So we have a single stage amplifier with few components. Which of these components are helping us to prevent the RF signal leak to the DC supply chain? Did everybody answer? Yes? Okay. So if everybody answered, I will pause this. Okay. Okay. So, as I mentioned, this inductor and this inductor, if we select the value properly, then they can show a high resistance in the operating frequency. Then the RF path, which is this path, so this is your RF path. So then the RF path can be just blocked to go through this line, and I mean go to VCC, or go through this line to go to VCC. Also, these capacitors could be selected in such a way that in high frequency they show a impedance of 0. So ZC equals to 0 in high frequency. And again, this one. So they also can help us to damp the RF signal and does not let the RF signal is going to the DC. So the B is correct. But this capacitor, these two capacitors actually are helping us to isolate the biasing circuit of our stage from the biasing circuit of the next and previous stages. So these two does not let the DC is going to the next stage or DC is going to the previous stage. So the correct answer is actually B. All right. So we have an antenna and we have a load. And I want to match these two with a matching network. So which of these matching network is not applicable here? I mean, which of these matching network I can use? I cannot use actually to match this load to the antenna load. Does everybody answer? So if you've done, then I... So, as your friends try to change their answers from correct to the wrong one. So, all right, we have a ZL here. So this is what we mentioned. We have a ZL, and the real part of this ZL is 25 ohm. So we have actually RL of 25. And then we have a RS of, so RS or RA, R of antenna is 60, R of the load is 25, and then we need a up conversion. Okay, so this matching network should do the up conversion in total. So high network could be up conversion or down conversion. Always it could be. T network could be up conversion or down conversion based on the value that we select at this R here, the R that I told you that we need first to match to the imaginary R. This R could be up conversion or down conversion. But the L network, so this L network is a down conversion L network, and this L network is up conversion L network. So we cannot use a down conversion. I mean, this network cannot convert a resistance of lower to a resistance of higher value. So then A is the correct, because we mentioned which cannot. Okay. And then I think the last question is based on the mixers, and we didn't cover that yet, so I will keep it for the next session, that one. But I think we have 4 minutes, so we continue to the lecture, if you don't mind. If you don't mind, we continue one more slide and then we finish, because I think we are a bit behind the schedule. All right. So back to the mixer, and the first type that I said that if we use a nonlinear system, then we can generate a frequency in the output which is not available in the input, not in RF, not in LO. Assume that in this equation that I said that it is a sigma of different components, okay? Different, it's a polynomial with different, it could be any order. If we assume that it is only a second order, I mean it's following a square law. So a square law is just a second order and no more orders. I will say that, okay, this could be correct in most of the cases. I mean, in the BJT and CMOS, we can say that this is correct. Then if our input is the addition of our RF and our LO, and then we send it to the square law, the components that we get in the output, a square law means we assume that C naught equals to 0, because I said that we can filter this one, the C naught with the AC, and then the C1 is not 0, C2 also is not 0, and then the Cn equals again to 0, N is not 1 or 2. We have only these two components. Then we have 3 elements. The fundamental frequency, I mean the frequencies that we have in the input directly go to the output. And they are coming from here, the C1 multiplied by this. we have the square frequencies, which is coming from here, C2, and then we have the cross modulations, which comes from here. If you just write down this V in C1 multiplied by this plus C2, this squared, you will see this one. We have three types of elements in the output. The fundamentals, the square, and then the intermodulation between these two. I mean the multiplication of these two. These two terms, we are not interested, and this is what we want in the output of the mixer. Okay? This is how we can generate the multiplier of